5.5 is talking about roots of real numbers. And this, again, has that concept of opposite operations. If you think about the root as being an operation, I think it helps clarify things. So if you think about n squared, that's the opposite operation as taking, to undo it, I would take the square root of n. Okay? If I want to undo the cube root, or the n cubed, I cube root it. If I want to undo the fourth power, I fourth root it. So these are opposite operations. So if n is your base, what this chart is showing you is really your numbers raised to those powers. And so you can quickly see how your numbers get bigger a lot faster. And these are your perfect, everybody remembers their perfect cubes, or perfect squares. Perfect cubes you maybe know to, maybe right there to 5 cubed. Fourth roots, maybe not so much. Fifth roots, if you know 32, we know the twos. But these are important numbers to kind of have handy. This table is a nice thing to have handy. When we are simplifying, remember when we take the square root, we always get plus and minus. And remember the operation of a square root is asking us to find perfect squares. So when I see 16, I know that that is 4 times 4, or 4 squared. X to the 6th, I could think about in groups like that. So if square rooting and squaring cancel each other, in essence, that means that I can do that operation and it's going to move outside. So if you just want to think about, if you have 3 plus 5, everybody writes 8. Nobody wonders where that plus sign went, because we know we did the operation. So the square root of 4 squared I really have a rule that lets me do this. The square root of 4 squared cancels, it leaves 4. The square root of x squared cancels, I leave x. The square root of x squared cancels, it leaves x. Square root of x squared cancels, it leaves x. So my answer is 4x cubed. Now another way you could think about this is the square root of 16. Now remember, we're looking for groups of 2. I could write it as x cubed squared. So then the square root of 16 is 4. The square root of x cubed squared, the squared and the square rooting cancel, and it leaves x cubed. So we get the same answer with maybe a little more work between. Now this one has what is essentially a -1 out front. When there are coefficients out front, it works a lot like our variables. As everything comes out, we're going to multiply it by -1. Now this looks really kooky. Now, you cannot take the square root of a sum or a difference, because remember, this is a single number. So I can't, it is not the square root of a squared minus the square root of 4. That's a no-no. That doesn't work. It has to be treated like a single number. But here I do have a single number to the 4th power. So I really could think about this as q to the 3rd plus 5 squared squared. So I still have 4. So if I take the square root of it squared, then I'm left with the square root cancels, that square cancels, and I have q to the 3rd plus 5, the quantity squared. Because if you think about it, there were 2 groups of 2 under there. The square root of something squared gives you the something. The square root of something squared gives us something, and when you're done, you have 2 of them left. Don't forget that negative sign that was out front. Now, this one is looking for the 5th root. So I need to find factors that show up 5 times. So this is where a factor tree comes into play and is really nice. If you have the table, you can see that this is 3 cubed. but I maybe don't have the table. So I know that 3 goes into this. 3 goes into this 81 times, prime number. 81 is 9 times 9. This is 3 times 3, and 3 times 3. So I have 1, 2, 3, 4, 5. I have 3 to the 5th when I factor it. A to the 10th I could write as a squared, and I have 5 groups. 2 to the 5th, power to power is 10. B to the 15th, that means I have b cubed, but I have 5 of them. And so when I think about taking the 5th root of 3 to the 5th, the 5th root and the 5th power cancel, leaving 3. The 5th root of a squared to the 5th, the 5th and the 5th cancel, and it leaves a squared. The 5th root of b cubed to the 5th and the 5th root cancel, leaving b cubed. Now, -4. So when I look at this, I say to myself, well, what number, what times what would make 4, -4? And in fact, you cannot take the square root of a negative number, so there are no real solutions. Because there's no two numbers that are identical that when I multiply them together I make a negative, because if they were both negatives it would be positive. If they're both positive, it's positive. So you can't get a negative square root under the radical sign. Now fractions, we have a cool property that says I can split it, and I can take the square root of the numerator over the square root of the denominator. So the square root of 1 is 1. The square root of 9 is 3. And so that's all there is to that. Cube roots, I can do the same thing. The cube root of 1 over the cube root of 64. If you're using your table, you know that 64 is 4 cubed. So I have the cube root of 1 is 1. The cube root of 4 cubed is 4. You can test this by raising 1/4 to the 3rd power, and you'll get 1 over 64. Here, I have the square root of 4 over the square root of 9, which is 2 over 3. Cube root, remember 8 is 2 cubed, cube root. 27 is the cube root of 3 cubed. Sorry about that. The cube root of 3 cubed. Cube root of 2 cubed is 2. Cube root of 3 cubed is 3. Again, if you want to check it, take 2/3, raise it to the 3rd power. 2 to the 3rd over 3 to the 3rd is 8/27. So you can see that you end up back where you start. And again, cannot take the square root of a negative number. Now you can take the square root or the cube root of a negative number or the 5th root of a negative number, but you can't do it with an even-powered root. Our next set of examples look very complicated because they have the 6th root of t to the 6th. There's another property, if you remember, the nth root of a to the nth can also be written as a fractional exponent. So sometimes when you have these exponents, it's easier to think about writing it that way, t to the 1st. If I go over to this one and I think about doing it that way, I have 243 times x plus 2 to the 15th over 5, to the 15th all to the 1/5 power, turning that fractional root into the root into a fractional exponent. Now this could get distributed, so I'm going to have 243 to the 1/5 power times x plus 2 to the 15th to the 1/5 power. This piece isn't very easy to handle, and you may want to go back to the root. This piece, power to a power, is awesome to handle. Now if you remember that 243 is really 3 to the 5th to the 1/5 power. Power to a power, I've got x plus 2. 15 times 1/5 is 3. That cancels. I have 3 times x plus 2 to the 3rd. You certainly could pull this back and say the 5th root of a whole number is easy enough to do. You can also change it into its root, into its base power, and use that power to a power property where you multiply. That is all there is in 5-5.